Okay. Welcome, everyone, to what is actually the final side event this year at COP27 at the Cryosphere Pavilion. It feels a little surreal to be at the end of these 2 weeks, and it feels almost equally surreal to see so many people actually physically here at this time when, as those of you who are here in Sharm el-Sheikh will know, they're breaking down pavilions all around us. But we're keeping on going, and the pavilion will actually be here and operating all the way until 6 p.m. this evening. So thank you for coming, and thank you to those of you who are watching online or perhaps after the fact, because these are all recorded, and all presentations at this pavilion, as well as the COP25 and COP26 pavilions, are available on our YouTube channel online. My name is Pam Pearson. I'm the director of the International Cryosphere Climate Initiative, and it is my great pleasure to welcome, as this final event, something focused on an effort that is really meant to bring the science of cryosphere connected to adaptation, connected to what communities need to know about different futures that we face depending on our choice of emissions pathways. ICCI is quite honored to be one of the advisors to this group. But we'll leave it to one of our speakers, Uta, to give a little bit more information about this. So without further delay, it's my great pleasure to introduce Dr. Carl Schleussner of Climate Analytics, someone with whom we've worked for quite some time in terms of helping to project levels of sea level rise at different emissions pathways. Carl, if you're available.
Thank you, Pam. Yeah, and a very good morning to Sharm el-Sheikh from
Okay. Okay, pause for a second till we get you on the screen up here too. Here we go. Okay, your slides are up.
Well. Yes, looks very good.
Yeah, thank you.
Well, then again, a very good morning from my side, and thank you very much to Pam and her team and the Cryosphere Pavilion to have us and give us the opportunity to present here. Indeed, we are very excited to have this opportunity. I wasn't aware this is the last presentation, so even more so now. I am very happy to kick us off on what I hope will be an exciting side event, and I'm looking forward to discussions as well, together with my good friends and colleague Fabien Maussion and Uta Klönne, who will present more in-depth results of some of our work that is ongoing. And I want to present to you some more general considerations around how we look at cryosphere risks. How should we do is make assessments of how we avoid bandwidth thresholds for the cryosphere, and specifically some insights from a project called PROVIDE that I have the pleasure to lead, and we are collaborating closely there with the Cryosphere Initiative in order to provide new perspectives on how we look into cryosphere risk, in particular on the scenarios of potential climate overshoot, something that we all, I think, very much concerned about. So if we look at cryosphere risks, we need to acknowledge that a couple of elements of cryosphere risks are really of particular concern and require great reflection in terms of the approach and how we should look at them. So we do know that there's still very large uncertainties due to very complex physical processes involved, due to short observational timelines that we have for many of the systems, due to but also unknown processes that we are still uncovering to date, and this really calls for a precautionary approach to how we look at such irreversible risks. At the same time, apologies. At the same time, the response in cryosphere is time lagged, so we don't exactly directly see what we are causing. We will have very, very far-reaching consequences, a big legacy of our actions to date, which again calls for precaution. And of course, and then I don't need to convince any of you in the audience here today about this, the importance of the cryosphere cannot be underestimated. This is of immense local as well as global relevance. And why I say local relevance, I think we often look at cryosphere risks in terms of global sea level rise, in terms of crossing thresholds of the Greenland or Antarctic ice sheet. But what we also need to acknowledge is that changes in cryosphere components such as permafrost melt or also glacial loss can have very, very concrete and potentially far-reaching consequences for local communities that are living around those systems or with those systems. And I think that's something we also very much want to take into view. What do I mean when I talk about these risks and how our consequences and legacy are relevant? I want to present some findings or a framework that we published back in 2018 with Matthias Mengel and others in Nature Communications, where we looked into different scenarios that peak between 2020 and 2035 and then have steep emission reductions thereafter. So this is the CO2 emissions front that you see on the very top. And then we looked at the long-term sea level outcomes of those different emission scenarios. You're all very aware that questions on when emissions going to peak is one that is also really, at the forefront of some of the discussions in Sharm el-Sheikh over the last 2 weeks and so. So what we do have at the bottom is a sea level rise observed to date of around 20 centimeters over the time frame of more or less 250 to 300 years. And now these scenarios, they look very, very alike in terms of the questions of how it looks like in the near term. But if you now zoom out to 2300, what you find is that our legacy under such scenarios for global sea level rise is very, very significant. So every 5 years, we delay peaking in global CO2 emissions, all other things being equal, the same effort made thereafter to get to net zero CO2 or to net zero greenhouse gases, we will commit about 20 centimeters sea level rise in 2300. That's an irreversible commitment. That's our legacy for the future. That's the legacy for delay. And this is our central estimate in a high risk case where we are indeed crossing dangerous thresholds for the cryosphere. Sea level rise commitment could be much, much higher. So our central estimate for if we peaked in 2035 would be 1.2 meters. If we were crossing dangerous thresholds of the cryosphere, this could be up to 3 meters. It is important to acknowledge that these projections are not yet based on the latest insights of the IPCC 6th assessment report, and we'll get an update on those a little bit later. But I think they set the scene very nicely in order for how do we need to think about cryosphere risks and what are the factors that we need to take into account and how do we want to approach those questions. So I want to move on to the question of, do we have the right tools to actually look at cryosphere risk and present them well and make sure stakeholders and policymakers understand how we should look at them and what should guide us in terms of the need for urgent and stringent mitigation actions. And it might be a little bit technical, but bear with me, and I hope you understand a little bit the conceptual, or I can talk you through a little bit of the conceptual dimensions that we think are important and that we want to tackle in greater detail. So if you see those cones here, with dots and then cones going left and right, they indicate some like uncertainty increasing from emissions, so emission scenarios as we assess them, or emission benchmarks to the very left in blue dots, to all the way to the uncertainties in climate forcing and the geophysical dimension and then the societal impacts all the way down to the right. What we are normally interested in is not necessarily the blue or the purple dimension. What we're interested in is normally the pink or the brownish dimension. So we want to avoid societal impacts, we want to avoid geophysical thresholds. So our cryosphere threshold would sit right here somewhere. And we want to avoid crossing that threshold. And now we want to ask ourselves, what do we need to do to avoid that threshold? And if you looked into this in the scenario space, you would see that basically because we look at emission scenarios and then we have 4 of them or 5 of them or maybe a few more, we might just have an overlap and say, well, yeah, it could happen under this scenario, it could happen under this scenario. Most probably, it would probably happen here and there. And it doesn't necessarily convey the message, what do we need to do in order to avoid crossing that threshold, or to have a good chance to avoid crossing that threshold. And I think that's exactly something that we want to get to, and that we think requires a bit of a different perspective on how we look at emission scenarios and how we do make our assessments. And what we want to look into in the context of the PROVIDE framework, we call this the reversal of the impact chain. We want to look at such geophysical thresholds or societal limits, such as limits to adaptations of communities on the ground, and ask ourselves, what do we need to do in order to not cross those limits? And what does it mean for our emission mitigation efforts and emission reduction efforts to give a good chance of not getting there? So we want to set those thresholds, and we want to work our way back, and we want to ask ourselves, what are the efforts that are required? And I'm sure you will get a few insights today from the next speakers that provide some tangible insights on what this would mean in very concrete terms. But just to set the scene a little bit, I think that's a philosophical approach that we are taking in order to really put cryosphere risks, given their far-reaching and dramatic consequences, at the center of our risk assessment, and ask us, what do we need to do to not get there? I want to illustrate what this means and how substantial these uncertainties are, and giving you another example of certainly not low relevance, but a little bit not a cryosphere, directly cryosphere related dimension, which links to the question of how to interpret the Paris Agreement temperature goal and what uncertainties have to do with it. And I hope it gives you an idea, or it helps to conceptualize a little bit what we're thinking about here. So if you looked at the Paris Agreement, and I think all of you in the room are very familiar with that, we do know the two elements of the long-term temperature goal: to pursue efforts to limit the temperature increase to 1.5 degrees, and while at the same time holding the increase in global average temperature to well below 2 degrees. And then there is the Article 4 that sets out how to achieve this by achieving net zero greenhouse gases in the second half of the 21st century. And what is important now is that the dimension of the temperature goal, the pursuing efforts to 1.5 and holding warming to well below 2 degrees, are part and parcel of the same goal. They're not two different, completely distinct dimensions, simply because there's a large overlapping uncertainty range as well. And if you plotted this, or if you showed this on a graph, so we now on the x-axis, we have the probability of exceeding 2 degrees over the 21st century, and then on the y-axis, we have the probability of exceeding 1.5. We can map this space out a little bit. We can say we don't want to have a likely scenario to exceed 1.5 ever, so we want to keep 1.5 within reach, as the IPCC would put it. At the same time, we want to stay well below 2 degrees. So we want to have, in IPCC terms, a very likely chance to never exceed that level. That would be a 90% likelihood. And now we map the scenarios of the IPCC 6th assessment report into that space. And what you see is actually that indeed scenarios that have a chance of keeping 1.5 within reach, most of them are also very likely below 2 degrees. So in order to adhere to both elements of the long-term goal and incorporate our substantial uncertainties in the climate system response that we still have to date, we should acknowledge that there's a double and part and parcel criterion in the Paris Agreement saying we need to pursue efforts to keep to limit warming to 1.5, which is on the y-axis, and all the time hold warming to well below 2 degrees, which will give us a high probability of, even under the worst climate outcomes, never to exceed 2 degrees. So this is a little bit of an excursion in that we have already looked into under this project and published in the publication earlier this year, just following up on the IPCC report. But now going back to the cryosphere dimension, so now if we set our cryosphere threshold here, so we have set a temperature target, and we can also now, of course, look into this on the questions of a cryosphere threshold, and I think that's very much what we want to explore in this side event going forward. And then we need to acknowledge, and this is an illustrative dimension, but we need to acknowledge that there will be an unavoidable risk already today. So we We are touching the systems. There are time-lag responses. We are already seeing unavoidable risks emerging, and we need to understand that. At the same time, we need to really know what are the avoidable risks still today, and we need to have a very clear understanding and be able to communicate them very well. And I'm looking forward to Fabien's presentation already, because I think there's a very strong insights there for what it means, what can still be avoided by global climate action, and how the unavoidable and the avoidable are really dimensions that we need to map out very, very clearly. And then on the very long run, we will have potentially irreversible outcomes that will be independent and from our actions. And even if we were to draw down temperatures again, cannot be reversed. While on some other fronts, we might see some reversible dimensions that we also need to understand a little bit better. But this is a way to look at cryosphere risks if we understood that we want to look at them from their risk perspective to start with, that I think is important and can help us in conceptualizing. So how do we plan to do this on this project? So I'm not gonna talk you through details, but I certainly want to advertise the project homepage and the general focus of our work. We are 1 year in the project. We have 2 years more to go. We hope we have ever more results along those lines of elements that I have outlined. And in particular, we do have an online dashboard where all of our results going to be included and can be explored. It's called the PROVIDE dashboard, and you're very much invited to look at the URL that's in the bottom left, climate-risk-dashboard.climateanalytics.org, where you can explore right now just a beta version of the tool, but with already some of the conceptual ideas. You can explore tail risks of scenarios, and indeed already some approaches on how to avoid crossing or how to avoid certain thresholds already. And it will be extended going forward, so really watch that space, including with many cryosphere variables. And we are working very hard on that, and hope to be maybe even back at the Cryosphere Pavilion with further results on our work going forward. I hope this gives a good dimension or a good setting the scene introduction for what's following now. And I'm looking forward to the rest of the event. Thank you so much for having me.
As I understand, Carl is needing to go after his presentation. So if there are any questions, we'll actually take them now before the next 2 presentations. If there are no questions, we'll just go ahead with these 2. And I think that Uta especially will be able to answer anything for Carl. But these are the goals of the project, which are really needed. So please, yes, Fabien Maussion, who is a wonderful glaciologist. We had him very hard at work yesterday, giving multiple presentations, especially on African and tropical glaciers. So please, welcome. The floor is yours.
I know how to handle the microphones now, yeah. I'm just waiting for the presentation to fire up. So Carl made a perfect introduction to our goals in the project. And so what we are going to do now is to zoom in one aspect of the cryosphere in particular, which is mountain glaciers. So in this presentation, I'm not going to talk about the big ice sheets, but about all the ice bodies in the mountains of the world. And this includes also the large ice bodies surrounding the big ice sheets. And so we are going to use the ideas that Carl developed in the project to actually put a cost to our CO2 emissions in terms of ice loss. And I'm going to try to turn this around into a more positive message. As Carl pointed it, there is room for action, and there is room also to save a lot of mountain glacier ice. So mountain glaciers have been one of the most important cryospheric components to sea level rise over the past, and they are going to continue to be relevant in the near future. Before the big ice sheets, which have a very different response to climate change are likely to take over. They also are important for water resources, for many downstream communities. They change the seasonality of runoff, and they are a buffer for droughts in many mountain regions of the world. They are accelerating right now at a large pace. And so one of the messages that you are going to receive from me as well is that there is a certain part of glacier ice loss which is already unavoidable, but every additional emissions we are going to put on top are going to have an impact. And so to study this, we use very similar scenarios that the ones that Carl presented. We are going to explore a range of outcomes. The reason we do that and go away from the SSP or SCP scenarios, which are very, very well developed, but that's only for maybe a few more of them. Here, we have a way to explore all much larger possible of outcomes by actually exploring scenarios where we continue to raise our emissions at the current rates and then peak at given dates, 2020, 2025, and up to a very pessimistic world where we would peak emissions only in 2050. And then we explore further annual reduction rates. So here again, provided by the literature, a range of a relatively low reduction rate of 0.3 gigaton per year, up to a very high reduction rates of 0.7 gigaton per year. And then, to make the picture a bit more complex even, we are actually exploring two big categories of scenarios. The one on the left are a world where we reach net zero CO2. And what does that mean is that we have slightly negative residual fossil fuel emissions, which are just compensating from emissions from land use, from positive emission from land use. But we still have residual emissions from other greenhouse gases, which we know already today are very hard to avoid from heavy industry, from agriculture. In a better world, we would reach net zero greenhouse gas, where these residual emissions, which are unavoidable, are actually taken care of by strong negative emissions, relying on carbon removal technologies. And so, to put this into perspective, maybe it's useful to go back to the very recent closing window, so UNEP emissions gap, where countries are actually classified in whether or not they have net zero greenhouse gas targets here in green on the map. So this is, for example, the UK or the EU, Japan, which have clearly stated they want to reach a net zero greenhouse gas where all emissions are summing up to zero. Other countries, however, have not specified which of the two they want, and even some countries like South Africa very clearly said we actually have a net zero CO2 target. And so with this suite of scenarios, we are able to explore a very large possible range of outcome. And this is already visible then in the temperature projections according to these scenarios. So this is global mean temperature up to 2300. And these scenarios then encompass scenarios which are staying below 1.5, maybe not statistically significantly below 1.5. None of the scenario is actually guaranteeing us to stay below 1.5 with 66% probability, up to a warming of approximately 3 degrees, which is more or less the current NDCs. And then once we have reached net zero CO2, the temperature stabilizes because we have residual emissions and the ocean is taking a little bit of the heat of these residual emissions. Only in a net zero greenhouse gas world where we really have completely zero emissions, then is the world starting to cool because we have heat uptake, CO2 uptake from the ocean. The cooling, though, cannot be expected to bring us back to a pre-industrial level in a few years. We are talking about still centuries to get there. Okay, but this is not my goal here. So what we've done then is actually to feed this information to a global glacier model to provide projections of glacier change according to these scenarios. And so this is what we are going to look at now in more detail. This is the main outcome. Again, you've seen many lines during these weeks, and so these are several more that I'm going to show, and I'm going to try to pitch you through how to analyze this data. On the right-hand side, you have the relative volume loss relative to today. So what you can already read from this graph, looking at the right-hand side, is that by 2300, we are going to lose 40% of glacier ice even in the most optimistic scenario. But you can also see that we have a wide range of outcomes depending on how we act in the future. The scenarios which are staying below 2 degrees with a higher probability, already there is a large range of outcomes, somewhere between 40% or close to 60% of global glacier change. And so what it says is that every incremental tenths of degrees already matter. What you can see also is that the rate at which sea level will rise in the future from the glacier contribution also strongly depends on the scenarios, with a more pessimistic scenario leading to a stronger annual sea level rise. Unfortunately, one of the last messages you can see from this graph is that even if we stabilize temperature, then the global glacier volume is still going to contribute and we are still going to lose mass by 2300, even if temperature stabilizes. This is due to the very large ice masses close to Antarctica and Greenland, and the ice sheets. Scientists are aware, I want you to know that the ice sheets have a response time even longer than that, several millennia. So this brings me to one of the first main message, is that, okay, we have a committed loss already, and this is 25% of all glacier volume by 2100 and 40% by 2300. What we can then do is also explore the outcome in a maybe more quantitative manner by putting lines, vertical lines here in this graph, and having a look at the scenarios which are going to explain us a little bit more about what to expect according to the different scenarios and reduction rates. So here, this is an example of sea level rise to expect in 2100 in the most positive case, where we would actually reduce our emissions now. Still time, it's not 2025 now, it's still time. And here already you see you have a range of outcome which is according to our total emissions. If we decrease our emissions rapidly and we reach a net zero greenhouse gas world, then actually we have the most positive outcome possible in 2100. And if we are slow and only stabilize and do not cool the climate, then we have a more negative outcome. So we are here below already. So we're talking about 5% of glacier volume difference if we follow all these possible scenarios. And then we can do the same by looking at the left scenarios, which have a much wider range of outcomes, of course. And here you see, for example, also one thing is that there is no difference between net zero greenhouse gas and net zero CO2 here, because if we start reducing emission by 2050, you don't see any difference in glacier response by 2100, even if we start having negative emissions by then. So this already sends a message that negative emissions are even more useful for glacier change if we start them early. Okay, and then we can do that for all the scenarios in 2100 and in 2300, when the range of outcome becomes larger. So I could spend hours on this graph, but we are all tired. So I'm just going to help you notice here that if we keep all other characteristics equal, we can see that we follow more or less a line across the year of peak emissions. So let's say we agree on a reduction rate of 0.5 and a net zero greenhouse gas world, and more or less we're on a line, which is kind of surprising, but sometimes complicated things can be simplified to a line. And then this is the main message of on my next slide here, is that we have a committed MICE loss, but from there, any additional year in delay of reducing our emissions of mitigation will cost an additional 1% of glacier loss. So you can make the math, and every day then it's going to be a tiny, tiny percent, but every day we actually continue to rise our emissions, we are losing ice. And you can also turn this into sea level contributions. So this is one of the main message already, is that each year of delay actually cost us glacier ice. And so the question is, can we maybe quantify this even a bit more using the tools we have at our disposal here? And so using this chain of scenarios, we have a new way to compute glacier loss, which is not a function of temperature or the year. Here we are plotting total glacier loss in 2300. So again, the whole outcome in 2300, not as a function of temperature, but as a function of total emissions, which we know in our scenarios. Here it's total emission in CO2. And on the y-axis, the total ice loss by 2300 of mountain glaciers. And you see that total emissions, not necessarily the decrease rate, total emissions is the main explanatory variable for future glacial loss. And you can also see that while the curve is linear for a while, it actually flattens out. And this is not due to complex physical processes in the climate system. It's due to the fact that glaciers are a finite resource. At some point, if we melted them all in a mountain range, then if you raise warming even more, then you've lost them and it doesn't make any difference. So there is no particular threshold that we are aware of for mountain glaciers at the global scale. Each glacier individually, each ice cap somewhere in the Arctic will have specific thresholds, which is going to force them to lose mass eventually. At the global scale, all these thresholds are mixing up, and we are not aware of any very strict threshold on global glacier change. However, we are still very aware that, first of all, there is a big range of outcome, and if we start to put a cost then to our emissions, which is very easy to do since it's more or less linear, we are able to compute an ice loss per kilogram of emitted CO2. And so in plain words, if we emit 1 kilogram of CO2 today, it's going to cost us 16.4 kilogram of CO2 by 2300 over the world. And because of the curve is flattening in high emission scenario, this potential is actually much less, because if we start reducing our emissions way too late, then glaciers are already gone, and then we actually lose this potential. And so I've talked about glacial loss, but I think it's actually more useful to turn the message around and put it in a positive way, like Carl did. The arrows were going down. So what's the potential we still have to save ice? And this is formulated this way. So each kilogram of CO2 which is not emitted today has the potential to save 16.4 kilogram of glacier ice in 2300. If we start reducing our emissions way too late, then this ice saving potential halves. So our emissions today for glacier change matter much, much more than the next one, and in a negative way, because glaciers will already be gone. You might be interested also in knowing where this glacier ice is going to be saved, because maybe if you are doing good, and let's say you spare 1 kilogram of CO2 by eating less meat or not traveling, unfortunately, you have no choice of deciding where this ice is going to be saved. So I'm going to tell you where. And in the Alps, for example, because it's a tiny bit of ice, it's actually there that we have also the least ice-saving potential. However, in high mountain Asia, you have already quite a large potential of this 16 kilogram of ice. But of course, the main ice that we want to save is located in the Arctic regions, where we have the big ice bodies today. And for the last minute I have now, I'd like to also explore one question which has been given way too little attention. And when I speak to the audience in Austria, for example, in the country where I work right now, people are, but it's going to come back, right? Because it was there before, and we've seen this in the past. And here, unfortunately, I have not so good news for the Austrian people and living there, is that if we look at the Alps in particular, even in a world which is cooling, well, ice loss is going to be so large in these regions that glaciers are going to need centuries to actually recover. Individual ones maybe might be growing a little bit, but we are never going to see the ice volume we have today. So this is a plot showing ice volume would be today, and this is the change according to these scenarios. And so we actually have to say goodbye to much of our ice in the Alps. There is a difference between 10 and 30% according to the scenarios. And even if we cool, glaciers are going to grow only very slowly. There is a very simple explanation for that, is that you can melt a lot of ice each year. There is a physical threshold there, but it's actually very high, while glaciers to grow, they need precipitation. And if we don't expect big changes in precipitation and solid precipitation, we just can't get this ice back. There is better news, however, for high mountain Asia, where this is one of the regions where we have the most possible range of outcomes, actually, because glaciers there are larger, and if you don't reach these thresholds where they have retreated to very high locations, then feedbacks are able to bring them back in the very positive scenarios. And there we see very difference between 80% of ice loss in the most pessimistic one, up to almost no ice loss, 20%, 10% in the most optimistic scenario. So this is also where glaciers are actually very important to water resources, and this is where we still have a lot of potential of ice saving. This brings me to the end. It was a bit longer than 15, but I hope that you could bring some message home now from this presentation. And I'm going to leave my main message here, that each kilogram that stays in the ground still has the potential of save ice, even if we have a dire picture here to show in our pavilion. Thank you for your attention. I think we just do the questions in the end, very much, if that's okay. And then, so the next speaker is going to be Uta from Climate Analytics, and she's going to bring us back to the big picture.
Third presentation, please. Thank you. Yes, thank you. Yes, exactly. And as Fabien indicated, I will sort of take a bit of a step back and yeah, go back to sort of the message that we're all here for. So thank you. So yeah, we'll talk about emissions reductions needs and the cryosphere, and yeah, how this is our main message. Only halving emissions by 2030 can minimize the risks of crossing irreversible thresholds in the cryosphere. So yeah, to start, what our perspective kind of is that emissions pathways as assessed by the IPCC Working Group 3, this is what kind of our starting point, what we're looking at, have a range of possible temperature responses. And this substantially increases the risk of crossing thresholds in the cryosphere, even under low emissions pathways, which is what we're going to show in a second, due to the risks of high warming outcomes, even under these pathways. Even closer, okay, thank you, I'll do that. Great, thanks, sorry. And so yeah, these temperature ranges need to be explicitly considered then when assessing the risks of crossing thresholds. And this is all based on a commentary that we currently have in review. It's being accepted now together with the ICCI, Climate Analytics, and several cryosphere experts. So yeah, so our main message, or the current state, is that threshold risks increase with every bit of warming. I think we've heard this now as well from the previous presentations. And I guess, as you all know, Arctic sea ice glaciers across the world, for example, with what Fabien also presented, ice sheets in Greenland and Antarctica and permafrost have experienced losses over at least the last several decades. And there's also ocean acidification, which needs to be considered, which is a direct result of increasing CO2 concentrations in the atmosphere. And so with further warming, several of these cryosphere elements might be at risk of crossing thresholds. Does this take a second? Okay, thank you. Yeah, so, and please no pictures at this point because it's not published yet. Sorry, but it will be soon. So, so yeah, this is an overview of different cryosphere elements, which you'll see on the left, and on the x-axis you have increasing global warming levels. And so, yeah, the message here is that for the cryosphere, threshold risks increase with every bit of warming, and some losses are irreversible, as Fabien's also made clear, on centennial or even millennial timescales. Okay, let's see. And so, yeah, to go a bit in detail, Fabien's already talked about glaciers, but to look at, for example, Arctic sea ice, it will continue and possibly accelerate through feedbacks, and there will be, yeah, potential abrupt loss of Arctic winter sea ice. Then there is limited evidence of a complete loss of the Greenland ice sheets between 1.5 and 2 degrees, but above 3 degrees, near complete loss will be irreversible over millennia. And then, yeah, an important message also on sea level rise here. So ice sheets crossing thresholds would lead to accelerated melting, and this could commit us to rising sea levels for millennia. And so yeah, now the purpose of our commentary also was to look at how these thresholds overlap with climate response uncertainties. And so what's important to consider here is that there remain substantial uncertainties in how exactly the climate system will respond to increasing emissions. And so, yeah, when assessing the risks of crossing thresholds in the cryosphere, this needs to be considered alongside the threshold uncertainties. And so, yeah, this is, I'll paste the figure together in a second, but this is sort of the second the part is that it shows the temperature response to different emissions pathways. And it shows that there is a large range of possible temperature outcomes when accounting for scenario and climate uncertainty of emissions pathways. And so on the top, you see that even Paris Agreement compatible emissions pathways have a chance of reaching warming levels that are within the range of potential cryosphere thresholds. And then on the bottom, you see NDCs. This is all based on the IPCC Working Group 3 report. And in the middle, you see NDCs, even if they're strengthened after 2030, this pathway. And these would reach warming levels under which crossing thresholds is the most probable outcome. And so to put it all together, our figure to summarize this this overlap of the different potential thresholds in the cryosphere with the temperature ranges of emissions pathways. So this brings us to our main message. We also want to send a positive message, that is, if we do limit warming to 1.5 degrees in line with the Paris Agreement, we can safeguard against crossing thresholds. And there's also a bit in the whole overshoot context. So for how long temperature levels would need to be reached to trigger these abrupt or irreversible changes depends on the cryosphere system that we're looking at. And there are definitely risks under overshoot pathways, and these are a major research gap. And so, yeah, all in all, I guess we all know this makes a strong case for stringent mitigation in line with Paris Agreement pathways, and only those have a chance of avoiding critical thresholds. So that's it. Thank you. And I hand over to Pam.
It's a good thing we're coming towards the end of the period. So we're open now for questions, and I would say that a lot of the science that in this unpublished work has been published here in terms of where these thresholds lie. And the QR code will give you access to the online version, some of the science of which is here on our totems, or Toblerones as they're sometimes called. At other COPs, they were 3-sided. We decided to make them 4-sided simply because we're looking at 4 different temperature levels, or really CO2 emissions. And so this gives a sense of the choices that we're making at these different levels, and what the response in the cryosphere will be, and therefore what the global impacts will be. One of the things that happened earlier at this COP on Wednesday is the creation of a new, very cross-cutting group called Ambition on Melting Ice, on Sea Level Rise and Mountain Water Resources. 18 governments got together, and they're from both polar and mountain, but also low-lying regions. And so this is a connection. It's trying to make clear within the negotiations, as well as communicatively, really, to the general public, that what happens in these regions actually has its greatest impact in terms of numbers of humans and ecosystems impacted outside these regions, outside high alpine and polar regions. And also that once the cryosphere responds, it is essentially irreversible, as Fabien outlined in terms of glacier loss. We're looking at, hundreds to thousands of years to restore them, even going down to lower temperatures, which will take some time. So any questions to the 3 of us who are here present in Sharm, please?
Okay, thank you very much. Can you hear me all right? Yeah, okay. Well, first of all, thank you so much for those amazing presentations. Really, really, really insightful. So I'm Richard Jones from the Met Office in the UK. And I just have a question about the reference to the Greenland ice sheet, and that you will potentially have like irreversible loss at 3 degrees, but not at 1.5 to 2 degrees. I'm just wondering whether you have considered what you could call thresholds, like socioeconomic thresholds, because at some point, of course, you'll get a sea level rise of X meters or X centimeters, which is going to make coastal communities, cities in large parts of the world infeasible. Now, I would be really interested to know at what temperature the loss you would get, for example, from Greenland and other ice sheets would cause that socio-economic threshold or tipping point to occur.
I think that in some ways that's a climate analytics question and sort of what PROVIDE might sort of look at. But I would actually say that, you know, the graphics that you saw are highly conservative. And this is something I may talk to my PROVIDE colleagues about, because the accepted cryosphere science threshold for Greenland, if you look at the median, is 1.6. So it's actually much lower. Now, wide error bars, right, on both sides of that. But we also saw presentations last week of a paper that came out just, 3 weeks ago, that showed a new mechanism that and the reason, by the way, that threshold is, you know, it's a 3 kilometer high chunk of ice. And once the altitude is lowered through surface melting, it gets to a point where it's, you know, below the threshold. It melts more each year. And that has been thought to be the Greenland threshold. But this new paper looked at what happened to the ice sheet that was over the British Isles and Scandinavia and Northern Europe. And there you had a mechanism where there were channels of water eating down, I guess is the best way to put it, through the ice sheet. There were amazing graphics, and you can look at these presentations online. Where basically the ice sheet was being eaten away on the inside. And what scientists found is the record of these huge channels on the seabed, showing that that's how the ice melted away. And that could be a mechanism that could begin on Greenland as well, and might mean that the loss there could be a lot faster. Now, it's much less ice than Antarctica. It's, you know, only 6 to 7 meters. There'd probably still be some ice in the center unless it got really warm. But still, this was news, I think, to a lot of people in the community, that this is a way Greenland might actually contribute quite a bit of sea level rise earlier than thought. And that's a lot of what we're seeing from the ice sheets right now. So then, you know, when you get that socioeconomic tipping point, it's hard to say in terms of, you know, because it's also due to rate. And again, work that came out in 2021 by Rob DeCanto, looking at potential sea level rise from Antarctica, we're looking at rates of 5 centimeters a year. And most in, you know, the adaptation community say that those rates are so fast that you really can't adapt to them in any meaningful way. So I would say that would be seen as a definite socioeconomic tipping point. For example, if we're getting at rates centimeters per year, rather than the current, which I think is 3.8 millimeters a year. Yeah, because that's just too fast to adapt to. Uta, do you have any thoughts on that? I know that's mostly your colleagues, right? In terms of the socioeconomic. Yeah. Interesting question.
Could you just, first of all, again, thank you for the brilliant presentations. Yours was absolutely dead on. It was very, very convincing. I'm not a glaciologist or a cryospherologist in any particular way. But I think the point that is, to me, evident in his comment or question is that translating this data or into language that non-cryosphere specialists can actually grasp, using the same graphs and the same actual data, but translating it into language that people can grasp, I think would be enormously helpful in terms of storytelling and in terms of actually convincing a broader public of the importance of this, because it's extremely compelling. But it's the language and the way in which people actually hear it that's fundamental. I wonder if you could just comment on that.
That is sort of what we're trying to do with the State of the Cryosphere report and with these totems. And I'd be interested in your take on this. Does it need to be simplified, you know, even further? Because this is produced kind of for the policy set, right? So this is looking at people who are at these conferences, for example. So you know, do we need to tighten it even further? We do or we don't. Yeah, you could. Amy? Yeah.
In my view, and I'm a professor of medicine, so I have a very particular perspective on these things. But in my view, things should be made as simple as possible, but not simplistic. This is as simple as possible, but it's the language. It's not the numbers, it's the language. So using, for example, a socioeconomic standard or a socioeconomic, not metric, but terminology that can actually communicate, again, very, very compelling data.
Be interested in more, you know, on that later afterwards. But yeah, I'll just give you a simple example, which actually Fabien did in his later graphs, and we did very intentionally with our own regional glacier graphs. In some ways, those are the most compelling things that we show. Because when you talk about glaciers worldwide, if you just look at sea level rise equivalent, like in the first ones, you know, most of that is these are polar glaciers. In other words, they're not part of the ice sheet, but they're huge. And they're the ones that are mostly contributing to sea level rise. And they're the ones that respond last. And I would say what humans care about are the glaciers close to them. And so what Fabien is doing, you know, with Austrian glaciers, and another simple thing that we did that he also did in this graph, you don't talk about sea level equivalent. You talk about ice loss. And so we basically took the same data and flipped the graphs here, because normal humans understand loss of ice better than they do, you know, sea level rise, especially because the amounts are so small from these alpine glaciers. But, you know, if you live there and you're reliant on that as a water resource, then that's really important. So that's why in this AMI group, for example, the subtitle isn't glacier and snow loss, it's water resources. And that's because that's more, you know, socioeconomic language. That's how people see glaciers in most cases in snow. Fabien, please.
Thank you for that. I just had a very short comment on that because I forgot also to tell it during my presentation, but also maybe what helps sometimes is images. So in terms of sea level rise, I'm not very experienced in what helps people to understand also the timing issue of it. And yeah, 5 centimeters a year. I mean, this is unbelievable if that happens. But regarding to this ice, to a CO2 to ice conversion, I mean, what we did back in then is that instead of saying 1 kilogram of CO2, because even this is abstract, if you put this into other numbers, for example, if you put this, then the numbers, 500 meters with a regular car today is actually 1 kilogram of glacier ice. And so this is also an image which is... that's unbelievable, yeah.
Was that an actual figure? 500 meters with a car.
Because, 1 liter of petrol in a car, that's already 2.7 CO2 kilograms. So yeah, 500 meters, it's actually an actual number, yeah.
I think this is a really interesting conversation. I just want to come back on the sea level. I mean, I completely take your point about for those people who are living adjacent to or influenced by the mountain glaciers, to be able to communicate about what's going on with them rather than what's going on with ice loss. I think that's really important. But just to come back to the sea level rise point, so a couple of the other things that I've been listening to here, which relates to coastal, is around, well, the two things. One is around loss of heritage. Second thing is around impacts on loss and damage on vulnerable coastal communities. So you're getting, so one example was on the coast of Ghana, where they've got castles all the way along the coast. These are slave castles. Probably the Europeans would be rather pleased if they got washed away by sea level rise, but this is heritage. And this is going through a few centimeters of sea level rise, plus the sands being lost because of and then you've got the coastal communities who are who've got agriculture, which is now going saline, therefore the women who are tending the fields are now having to go and fish. This is a big change. and the children are now not getting educated as a result of that. So there are stories that you can link a few centimeters or millimeters of sea level rise to actual things that are going on for billions of people around the world. And we have to reach all of those people with our stories. So that's just to add on to that conversation.
Yeah. Can you hear me? Apologies. Yeah, and apologies for being the voice of the from the off. I had to go to put my little daughter to sleep, and unfortunately she did. So I was able to join back for the discussion. It's great to be actually again, and thank you so much for making those points, Richard. I think they're really, really excellent, because that's exactly where we want to get to under the PROVIDE project in this approach. So basically to not provide scenarios to people and say like these are things that might happen, but ask, okay, what are your local concerns? What are your local thresholds? What is exactly the local loss and damage you might experience, and how can these elements be avoided? What needs to be done in order to avoid them? And that's a framing to start from those societal thresholds and go all the way back into the emission space that I think we might do better in exploring, or also even showing things like the marginal benefit as Fabien has basically shown. So what can we do today, like one kilogram of CO2 less emitted, does this and that to a unit that you are actually concerned about. So we're not talking about global mean temperature, we're not necessarily even talking about global sea level rise, we talk about your coastline, the things that you are concerned about, and we try to link it all the way back to what needs to happen in terms of global transportation. So I think you make a really, really excellent point there. And if it's unfortunate that I can't be with you in person, I would really love to chat further with you all about this. But hopefully maybe there's an opportunity to follow up on this soon. I have to say on sea level rise, unfortunately, we do not cover regional sea level rise, as you all know. It's another level of complexity that we are not fully covering under this project, but we are trying to pursue exactly those approaches for local glacial loss, but also then for other climate variables like extreme temperature or precipitation, even down to the urban level. So we're trying to get there and try to get these conversations going. And I would really love to discuss or be in touch with all of you. Please feel free to reach out to us to see how we can join forces and try to develop exactly those narratives. And thank you for these precise and excellent comments.
Thank you. We have another question. I thought I'd also say, for those of you who aren't watching, the informal that was going to start at noon is now starting at 3, so plenty of time.
Thanks. It was just a question to bounce off James's point and also the gentleman behind me on, do we have a summary for policymakers that's been put in place alongside I haven't read the report yet, I'm afraid. Does a summary for policymakers exist? And if it doesn't, it would be really important.
What are you talking about? Are you talking about the paper or this? I would say this is entirely a summary for policymakers. What we do at the very back is the same information that is in each chapter, but it's by temperature. And so it gives the summary of what the effects would be in all 5 of the dynamics we focus on.
I was just bouncing off the point that was made on the language point and on the point you very eloquently made with the very physical 500 meter. Because as someone who works in the policy space, I can assure you that type of language, sadly, is the one that's the most important and the most effective, rather than the wonderful but graph-heavy alternatives. Thank you.
Yeah. I mean, what we do, and feedback would be very welcome. Okay. I'm going to talk about something we haven't talked about. This is permafrost. So at the very front of the chapter, there's summaries of the emissions pathways and what the response would be. So, this is often a work in progress. I'm already getting some ideas from you in terms of what we might be able to add in terms of these socioeconomic impacts for next year's report. So, feedback, very, very welcome.
Maybe just to make a very positive comment. This was the first booth that I stopped at on Monday when I arrived, and it's the last one before I leave. I read I picked up a copy of the Cryosphere report, expecting to be baffled by data. as has been the standard practice, over the last sort of 20 years of climate action. I was blown away by how simple, clear, and elegantly written that report is. It is a really, really good policy summary with very, very well articulated science and very well translated science into policy prescription. So it's a small comment. Congratulations. It's a great report.
Thank you. And that thanks goes to the 60 plus reviewers, a couple of whom are in the room, and editors as part of the ICCI team. So thank you. I appreciate that. It's what we try to do. If there are no further questions, I can see our sound man wanting to get to his other work. We really want to give a huge round of applause to the technical team that has supported this. So before he walks away, the guys in back, they've really been fantastic. Yeah. And thank you for coming to this event. We'll see how much this manages to then get into not just this negotiation, but follow-on ones. I've been going through the text of the cover decision, and I can see all sorts of places where a lot of this language across the board, whether you're talking mitigation, loss and damage, or adaptation, where these kinds of findings can be put in and maybe make it a little bit more real, perhaps in next year's cover decision. If you haven't yet looked at the ice sheets, Tobler, or also in the report, we actually point out where the next COP is physically located and what would be the sea level. Basically, again, going back to Rob DeCanto's work, you could have as much as 10 meters of sea level rise just from Antarctica by 2300 if those models are working correctly. And it's pretty decent work. It's the first of its kind. It's since been, same sorts of approaches, Chris Stokes on East Antarctica, in terms of looking at the dynamics of the ice sheet, not just, global models. But the coastline would run straight through where the COP is going to take place by 2300 under these high scenarios. So thank you also to our early career scientists, not all of whom are here, but we have Chen Zhao back there still from Tasmania and China, who has been here. Amy and Emma, who've been struggling with the technology. Emma's sitting here in the back for the entire 2 weeks and really supported this. Also recognize Jimena, who was in ECS last year and came this year and also very much helped out. From Mexico, you could say Chile in a way in terms of studies, and now it's Stirling in Scotland. So it gives a sense of the breadth of this community. And for those of you watching, again, thank you for your attention during this 2-week period. And hopefully we'll see you again at COP28. So signing off, I guess, for the COP27 Cryosphere Pavilion and on to the cover decision. And we'll see if this breaks the record for the longest running COP. They would have to go well into Monday to do that, but there are some bets on that level. So all of you here see, and the rest of you, you can get a few good nights sleep at least that we may not have. So thank you very much. Have a good conclusion to COP27.